Alright, we have relationships between position and velocity and between velocity and acceleration. Okay. Our basic sense is that velocity, for situations where the velocity is constant, or if we're averaging over all the motion, our velocity is equal to just a change in position over change in time. Okay. So our goal now is to try and understand, well, what does this look like graphically? If I were to graph some motion, how are these related on a graph? Let's go ahead and look at a position graph as a function of time. Okay, so we'll have x versus t, and x can be positive or negative. Okay, so let's suppose my position graph looks like this. Okay, it looks like that. So first question is, well, what is it doing? What is this object doing? Okay, well, I can see that at t equals 0, so right here where my two axes cross, it's at 0. It's at x equals 0. So I've chosen a coordinate system where its starting location is 0. And it gets bigger than that. It gets more positive. It moves in the positive x direction. So at this point in time, I've gotten to this position, which is in the positive direction. So if it's a standard coordinate system, my object has moved to the right. So let's kind of draw that. So I've got a coordinate system here. Okay, my object started here, and then it moved to the right to a certain point. Okay, right here. So here's my standard coordinate system. Okay. If we call this 0 and this t1, then this would be our 0 point or our 1 point. Okay, and then what's it do now? Well, as time ticks on from here to here, it stays in the same position. So this horizontal line indicates it's not moving anywhere. We're not changing our position even though time's changing. So I'm sitting there. So it sits there for a while. I'll make that dot bigger, I guess, to emphasize it's sitting there. And so it stays there from time 1 to, let's say, time 2. So this is t1, this is t2. Alright, then what is it doing? Well, now it's starting to move towards 0. So it's coming back here and keeps on going into the negative. So it actually goes further negative. Okay. And so we can show that that's 2, and this might be point 3, where this time here is 3. And then again another horizontal line. Time's ticking on, but it's not moving anywhere. It's not changing its position. And so it's staying still at that point for the remainder of the time. So that's how we can read this graph physically. Okay, it's moving, okay, and then it stops and moves the other direction and stops. So our question is, get back to here. Well, what's its velocity over this time? Well, here and here might be easy because we've already established that a horizontal line means it's not moving. Okay. Well, looking at this, that makes sense. Velocity is a change in position over time. Our time is non-zero, but our change in position is 0. It didn't change. And so a horizontal line indicates a velocity of 0. Okay. Well, what's this? This has a change in position, a positive change. It increases as time increases. So our change in position here is positive, and this time is obviously has to stay positive. And so we get a positive velocity here. Okay. There. Now over here, from this point to this point, I am going back towards 0, so my change of position is negative. I'm going towards 0, and time's ticking on, so that's doing its thing. And so for here, my velocity is less than 0. It's negative, and that actually makes sense because we saw it's moving in the negative direction, so a negative velocity ought to indicate that negative direction. Now, what about here? Well, I'm still getting a change that's negative. I'm more negative now than I was. 0 minus a positive number is a negative total. A big negative number minus 0 is a negative number. So here it's the velocity is less than 0 too. It's negative. Okay? And the way I've drawn it is the rate at which it changes is no different. So these two velocities are actually the same, because the rate at which it changed, how much it changed in how much time, was the same. So that allows us to say something a little bit differently. If no matter where we look, we can rewrite that to say our velocity is actually the derivative of our position as a function of time, because the derivatives simply mean slope. That's all a derivative really means graphically, is it's the slope of the line. The slope of this line is 0. Our velocity equal to the derivative of time, position in time, the slope of 0. Okay? If our slope is positive, we get a positive velocity. If our slope is negative, we get a negative velocity. And it doesn't matter if it's negative in the positive region or negative in the negative region. It's just the slope. That's all that matters. I could have had a positive increase in the negative region. It's still a positive slope. I'd get a positive velocity. And so there's all sorts of possibilities here, but the basic idea is that the velocity is equal to the slope on a position versus time graph. Okay? So that's how we can relate these two quantities together.